Okay, students, welcome to video class number 15. Now, in this class, we are going to deal with again the time domain analysis of a second order system, and that's labeled as part 2. Okay, so before going into this today's session, I would like to give you a recap of what we have studied in the previous video, that's in part 1. So we actually started with the second order system transfer function, which is given by omega n square plus divided by s square plus 2 theta omega ns plus omega n square, right? Now, then we have defined this omega n as the natural frequency of oscillation, and while theta to be the damping ratio. So we understood that this is the natural frequency is the frequency by which the system can oscillate, and zeta is actually the factor which actually prohibits this oscillation, or which is that process we call as the damping. Okay, so the damping is governed by this damping ratio. Now we have also, as we try to derive we started to derive the response of the second order system for a step input. So that's what we considered. Next is we considered the second order system with the input as a u of t, and we started to derive the c of t, right, by using this expression. Instead of r of s, we put 1 by s, and we continued our derivation, and we arrive at a result like this. C of t is equal to e raised to minus theta omega n t into divided by root of 1 minus theta square the whole into sine omega dt plus 5, right? So we went on to define this another term called as the damping frequency of oscillation, which is given by omega n into root of 1 minus theta square. Now this is actually an expression by the assumption that the theta. Now, what do you mean by theta? Theta we have called that as the damping ratio, and theta is a positive quantity. It can be. So we have also seen that there can be 4 cases. We will be studying that as 4 cases. That is where theta is equal to 0. Theta can be between 0 and 1, theta is equal to 1, and theta greater than 1. So actually this is a result where we assumed the theta to be in between 0 and 1, and we have also drawn the response of that. So at t is equal to 0, when you substitute t is equal to 0, the whole thing becomes 1. 1 minus 1 is 0. But we know that this is sinusoidal. 1 minus, as time progresses, this will come into play. That means as t increases, what we see is there is an amount of oscillation corresponding to the sinusoidal function. But another thing is that as time increases, exponential function will also determine its amplitude, the amplitude of the sine wave, and this exponential is a decaying exponential, which means that as time progresses, the oscillation also decreases. So this factor, this parameter actually aids the damping, right? So this one aids or helps the damping process, and this will ensure that this reduces to 0. So this is the case when theta is in between 0 and 1. Now coming to the error, we have seen that the error is nothing but e of t is given by it is r of t minus c of t, right? So it will be r of t minus c of t, that is the input minus the output response, and we found out that e of t to be this e raised to minus theta omega and t into root of 1 minus theta square into sine omega dt. Now at t is equal to 0, this becomes at t is equal to 0, what happens? This is equal to e raised to zeta, so this becomes equal to sine omega dt into, so this omega d can be written as what? Omega n into root of 1 minus theta square. So what will happen to omega dt when theta is equal to 1? Theta becomes 1 means this becomes 0. or this is equal to sine phi. Sine phi is theta. Theta we assume to be in between 1. So this will be sine phi, sine theta, cos phi. Okay, now coming to this, e raised to minus theta n into dt, what you will get, this is actually the error signal. Now when you substitute theta to be now at t is equal to 0, what happens is this parameter becomes equal to 1, right? E raised to 1, and this is theta is equal to no, that is 1 by root of 1 minus theta square into sine this is okay, sine phi. So you'll be getting the sine phi, right? So I'll just explain this. How will you draw this e of t at t is equal to 0? What is e of t at t is equal to 0? At t is equal to 0. Now, when you substitute, you will be getting this e raised to minus omega n into t at t is equal to 0. This will be 1 by root of 1 minus theta square into, what about sine omega dt? Omega d can be substituted as omega n into root of 1 minus theta square into t, right? Now, what happens when at t is equal to 0? This is sine 0, 0 plus sine phi. This will be into sine phi. Now, what is sine phi? Sine phi, we have assumed that to be 1 by root of 1 minus theta square into root of 1 minus theta square, which is equal to 1. So, at t is equal to 0, it will be having the maximum error, which is equal to 1, right? Now, as we know that this is an exponentially decaying signal, this will be decaying, right? So this will be decaying, but what we can see is this decaying signal, as t increases, what you can see is this will be decaying, but there will be a sinusoidal pattern. Why? The reason is due to this. As t increases, this will also come into play. That means there will be some amount of oscillation, and finally it reaches to 0. So it is just the exact opposite of the response, right? Now, as time increases, the response approaches to 1, meaning that the error is small. It's getting small, and you can, after a particular time, we can assume that this has reached a steady state. That means the error is equal to 0. Now, we have also seen one more thing called as a time constant, right? So when you try to draw this, in order to get some more points, we have defined a time constant, and how will you evaluate the time constant? Time constant is actually the time which makes this exponential power to unity. Now from this you can see that when t becomes 1 by theta omega n, this becomes e raised to minus 1. So this is defined as the time constant of the second order system. Now which now in this figure, which time you will decide as the time constant, as the settling time. I have also described about the settling time. Settling time is the time taken by the system to reach the steady state. Now in a practical system, in an ideal system, it will be always, the settling time will be always equal to infinity. There only it will reach the steady state. But in a practical system, we define the settling time in terms of this time constant 1 by theta omega n. So as I mentioned earlier, say this time constant can be either selected as 3t, or it can be selected as some 4t based on the tolerance that you provide. If the ts is selected as, if the ts, that is the settling time, is selected as 3t, then that is for a 2% tolerance, while if it is equal to 5t, then the designer is providing a 5% tolerance, which we have all discussed. So these are the things which we have so far studied in the previous video. Now we are going to start from that. Okay, now listen please. Now we are going into the case 2. We have already studied that this equation is derived under the assumption that theta varies in between 0 and 1. As I have already mentioned that theta is a positive quantity that can have values equal to 0, that can be 1 or in between 1 or greater than 1. Now the next case is theta equal to 0. What will happen when theta equal to 0? I am rewriting this expression again. So you can make use of this expression for this case again. So c of t by some changes as shown, right? E raised to minus theta omega n into t divided by root of 1 minus theta square into sine omega dt, right? So this is sine omega dt. Instead of omega dt, I'm putting this as omega n into root of 1 minus theta square, right? Okay, into theta square into t, that is sine, plus phi. Now what is phi? As I mentioned in the previous video, that phi is actually, what is phi? Phi is actually, this is it, tan phi is equal to root of 1 minus theta squared by theta, or from this you can get this phi to be tan inverse root of 1 minus theta squared by theta. You can substitute that. So substituting that, you will get this as tan inverse root of 1 minus theta square divided by theta square, right? 1 minus theta square divided by theta. So this is it. Now what happens when you put theta equal to 0? When you put theta is equal to 0, let us see. 1 minus, when theta equal to 0, this becomes equal to 1. Now what about this? This is root of 1 minus theta. So theta is equal to 0. This is 1. So this is 1 minus 1. Okay, so the whole thing becomes equal to 1. Now what about this? When theta equal to 0, this becomes, so this is tan inverse root of 1 minus theta square, or this can be written as sine omega n into, when theta is 0, this is 1, so sine omega n t plus, what about this, plus tan inverse, when you put theta equal to 0, this becomes root of theta, it is tan inverse infinity, which is, so this becomes tan inverse infinity, or you can call this as 1 minus sine omega n into t plus pi by 2, or you can rewrite this expression as 1 minus cos omega n into t. Now how will this c of t look like? This is 1 minus cos n omega n t, meaning, so you know that cos wave looks like this, right? Cos wave looks like this. Now if you do this 1 minus cos wave, then it will be like this, right? It will be ulta, right? It will be in the reverse direction, right? So what do you but there will be always a shift of 1, right? So by 1 it gets shifted, means, now it gets shifted means the signal gets, so the signal will be like this. You are going to get the c of t as like this, right? So it will be starting like this, and you have a wave coming like this. It is shifted by 1 unit because it is 1 minus, so everything gets shifted. You're adding this minus cos and omega t plus 1, so it gets shifted, and it will have a sine, a shape of a sine wave, but shifted by a 1 unit in the positive direction. So you can see that what happens at theta equal to 0. Theta equal to 0, the output is having a sustained oscillation. What's the meaning of sustained oscillation? Sustained oscillation is a constant oscillation. It is neither increasing or decreasing. It remains as such. It oscillates. Okay. Now, is it desirable for a control system? No, it's not desirable. But you will see that this is this point, theta equal to 0, actually divides the system, or it actually decides whether the system will move to the unstable position, or it will be in the stable position. So this can be considered as a stable position, because even though there is a presence of theta, there is a presence of oscillation. That oscillation gets damped, or this condition we call as the underdamped condition, right? This is underdamping. So theta so this condition, or this case, theta less than 1 can be considered as the underdamped condition, while this is the case where theta equal to 0, or you will call this condition to be undamped. That means there is no damping. Okay, undamped condition, right? So no damping, that means the system oscillates. Okay, so This is called as a sustained oscillation or an undamped oscillation. So this happens when theta is equal to 0. Okay. Now let's move on to the case 3, where we consider theta equal to 1. Okay. So the equation can be rewritten as, now C of t equal to 1 minus e raised to minus theta omega n t divided by root of 1 minus theta square into sine omega n into root of 1 minus theta square into t plus tan inverse root of 1 minus theta square by theta. Okay, now just let me just put theta equal to 1 into this equation. What will happen to this equation? This equation becomes, so this is when I put theta equal to 1, what happens is this becomes e raised to minus omega and t, but this is going to be sine of some infinity, so that's going to be infinity. So you're going to get this term here also. This becomes 1 minus 0. So this will be some infinity into infinity form, so you won't be getting a definite answer for this case. So in order to that, we rely on something called as, we will be finding out, try to find out ct, applying the limit as theta tends to 1 to c of t. Okay, so what is the principle behind applying limit? Limit at theta tends to 1 means when you apply theta tends to 1 as a limit, what we need to do is after cancellation only you will apply this limit. So I will just explain what it is. So I'm rewriting this, the whole expression here. Okay. Now from the okay, so this is the equation. I have written this equation and applied as theta tends to 1. Now in the previous discussion and the video, we have found out that we have assumed this phi to be tan inverse root of 1 minus theta square by theta. So you can replace that by theta, right? Now you can say that this is actually of the form, this is of the form sine a plus b, right? Now what is sine a plus b? So you can write this as sine a cos b plus cos a sine b. Okay, so you can write this. So in this form I can rewrite this as limit, okay, rewrite as, so we'll get this as 1 minus e raised to minus theta omega n into t root of 1 minus theta square sine a, considering this as a and this as b, you can write this as sine omega n into root of 1 minus theta square into t cos phi plus cos a, that is cos omega n into root of 1 theta square into t sine phi. Okay. Okay, so you can write this as sine omega n into root of 1 minus theta square into t into cos phi. What is cos phi? Cos phi, we know that we have assumed this theta to be equal to cos phi plus cos omega n into root of 1 minus theta square into t into this whole into, what is sine phi? Sine phi is root of 1 minus theta square. Okay, now I'm multiplying this. Okay, so you will get this as, now okay, now let us look again. I have rewritten this constant and okay, what about this sine omega n into root of 1 minus theta square into t? So this, the whole thing into 2 into the theta, right? Now we know that theta is, this is the case that we are considering, that means theta is more close to 1. So what will be the value of 1 minus to a value which is close to 1? So this will be very, so this part, that is omega n into root, is very small. And you might have studied in your lower classes that sine theta will be equal to theta when theta is very small. Okay, theta is very small, right? Okay, so why this becomes small? Because this is root of 1 minus theta square. Theta is close to 1, so 1 minus quantity will be it will be close to 0, right? So that means that becomes very small. So in that case you can rewrite this as cos theta. So sine theta can be written as theta. So what is the theta here? So the theta will be omega n into root of 1 minus theta square into t, right? The whole into, right, into theta plus, what about this? See, this is actually, this is very small. Now what can you say about cos theta? Cos theta, when cos theta is equal to what? When theta is very small. When theta is approximately small. Why theta is small? Because of the term root of 1 minus theta square, right? And this becomes very small or close to 0. Now as theta approaches to 0, cos theta becomes equal to 1. So you can substitute that as, so that the remaining term will be 1 minus theta square, right? Now in the next step, what you do is, again limit theta tends to 1 into 1 minus e raised to minus theta omega n into t divided by root of 1 minus theta square, okay, into omega n into root of 1 minus theta square into t into theta plus, again, so this is multiplied by this term, plus e raised to minus theta omega n into t divided by root of 1 minus theta square, right? Root of 1 minus theta square into what? Into this root of 1 minus theta square, right? Okay, so this and this get cancelled, and while this and this get cancelled, so the idea is to eliminate this root of 1 minus theta square. Why do we need to eliminate? Because when you put theta equal to 1, this becomes infinity. So somewhere or other we need to eliminate that. So you will be getting this expression as limit, say theta tends to 1, it will be 1 minus e raised to 1 minus e raised to minus theta omega nt into omega n into t, right? Into t into theta plus, what about this? You will be having this as e raised to minus theta omega n into t, right? Okay, so e raised to minus theta omega into t. Now this is minus, right? The whole minus. Okay, so you just make a correction. There is a bracket over here. We haven't that multiplied with this minus into this. So this is 1 minus of this e raised to minus theta into that, that gets cancelled. So you will be getting like this. Now you can write this as limit theta tends to 1 into 1 minus, okay, you have an exponential term here, so you can write this as e raised to minus theta omega nt as a common factor, right? So you got your common factor, right, as, and then that is 1 plus 1 plus 1 plus omega n into t, right? 1 plus omega n into t. Okay, so now substituting theta to be equal to 1, you will get this as e raised to minus omega n into t into 1 plus omega n into t. Okay, so this is your c of t for theta equal to 1. Okay, now there is a correction. So there is a theta here, this theta will be here. Okay, now once when you put theta equal to 1, now applying the limit, this theta and this theta gets equal to 1, so that you will get your c of t as this. Now when you try to draw this, there is now the speciality when you compare the c of t with the case 1, right? Okay, with the case 1, that is with this case, there is a sine term, right? But in this output you can't find any any sine wave, but you have a exponentially decaying function, right? E raised to minus omega n t, and we know that if you try to draw that, so what happens at c of t? So c of t and t, just see what happens. What is the value of c of t at t is equal to 0? Substituting t is equal to 0, this becomes equal to 1, and this will be, say, some this is t is equal to 1 and 1 minus omega nt, right? So this must be omega nt. So that means you have at t is equal to 0, this becomes equal to 0, right? This becomes equal to 0. Now this is equal to 1 minus 1, which is equal to 0. Now what about at c of t at t is equal to infinity? When you add infinity, this becomes 0 and it is equal to 1. So that means nowhere there is no, so at t is equal to infinity only it will be reaching 1, right? So before that there is no oscillation, but you are going to get a graph like this. That is, when you try to draw this, you'll be getting a graph like this, as we did in the first order system, right? Now it will be approaching to 1 only at t is equal to infinity. So under this condition, what you observe is there is no oscillation, okay, but it reaches the steady state. So what can you say about this condition where theta is equal to 1? So this condition, that is the condition where theta is equal to 1, is called as, what is this called? So this is called as the critically damped response. This is critically damped response. That is the case when theta is equal to 1. Critically damped. That means this is the case where theta is equal to 1. Now if it goes just less than 1, it will oscillate. So this is actually the demarcation point of the critical point, which actually pushes it to oscillation. That means, say to get this, so this is actually the value for theta between 0 and 1, and when theta equal to 1, this suddenly what happens is the whole oscillation gets vanished from the say output. That means it just relieved from the oscillation. That means there is no oscillation. So this is called as a critically damped response. So critically damped response, or this is the case where theta equal to, this is the case where theta equal to 1, right? Now next is case 4, where we consider theta greater than 1. So in this case we will be starting from the basic equation, that is one which we have already seen in the previous video, that is omega n square divided by s square plus 2 theta omega n s plus omega n square. Okay, now so what is R of s? So mind you that we are actually studying about the step response, right? The time response of a second order system due to a unit step input. So when your R of t is u of t, R of s has to be 1 by s. So you will get this as 1 by s into omega n square by s square plus 2 theta omega n s plus omega n square. Okay, now then the third step is what we have found out in the first video, that is, look at this. So we just converted this into this form, right? So that you got this as s plus theta omega and the whole square plus omega n square into 1 minus theta square, right? So you might be remembering. If you have any doubts, you may refer this video class 14. And what I took here is I've just taken a negative sign out of this. That's why here it is minus omega n square into theta square minus 1. Okay, now then what is this s plus theta omega n square? Just look at this. So this is actually a quadratic term, right? Now this quadratic term can be factorized. Okay, so how will you factorize this? The whole term is equated to 0, so that you will get this s plus theta the whole raised all square minus omega n square into theta square minus 1 is equal to 0, or bringing this side to this side, you will get this as, right? So what will be s plus theta omega n? S plus theta omega n will be the root of this plus or minus. Now since it is omega n square, in the next step it is written as plus or minus omega n into root of theta square minus 1. So what is your S? S can be minus theta omega n plus omega n into root of theta square minus 1, or it can be minus theta omega n minus omega n into root of s square theta square minus 1. So that now you can you can represent this as s minus s1. So you can call this as s1 and s2, right? That those are the two roots. So you can factorize this term can be written as s minus s1 into s minus s2, right? S minus s1 into s2. So in that way I have just written like this. Now this can be resolved as three partial fractions by a by s plus b by s plus this whole term, then plus c divided by this whole term. Okay, now the exercise is left to you to find out a, b and c. After finding out, and you will be getting a lengthy answer for a will be getting a you will be getting as 1, you will be getting a to be 1, and b to be 1 by 2 into this much, and c to be like this. A b will be minus, c will be plus. That's the difference. So you may just look at do it by yourself. I'm not going to do it. Okay, so anyway, now when you take the s minus, since these so the basic this thing will be a by, look at this, a by s plus b by s plus something plus c by s plus something. So this is going to be when you take the inverse, this will be a into plus b, say call this as s1, this as s2, right? So you will be writing this as e raised to minus s1 into t plus c into e raised to minus s2 into t. So you will be getting an expression like this. Now what does this suggest? These two equations shows that this is exponential in nature. That means what you're going to get is you're going to get a similar expression which we have just found out for theta equal to 1, right? So this is the graph that we obtained for theta is equal to 1. So now in this graph, if I'm going to plot this, right, I'm going to plot this, I'll be getting a graph like this, right? So what's the difference between these two? This is actually for theta, this is which we have already studied. Theta is equal to 1. This is for the case where theta is greater than 1. What does this show? Now comparing these two, which one is slower? Obviously this has to be slower, right? So this will be reaching at this point at this time, while this will be reaching only after some more time. So that means the system with a higher theta can be slower, but what is the advantage? In no chance it will be going to it will be having an oscillation condition which can make the system unstable. So such a condition we call as such a condition where theta greater than 1 is called as the over-damped response. This is called as a over-damped response. Okay, now in the next I will just give you a comparison of all these cases in a single graph. Okay. Now, so here is a comparison. So this is going to be a comparison graph of various comparison of a step response. Okay, this is the step response of a second order system, okay, for various values of theta. Now I am putting this theta as, say, is equal to 0.5, and this one is for theta 0.8. So now in these two cases, this lies in the case 1, right? So this is case 1. This is the case 1, that is where theta lies in between 0 and 1. So you get a graph similar to this shape. So that's why I have drawn in this shape. Now what do you infer from this? Now as theta approaches to 1, what happens is the initial oscillation will be having a peak, right? Now this peak of the oscillation gets reduced as theta approaches to 1. So that's a required thing, right? Theta is the damping ratio. As you increase the damping ratio, the effect of damping increases, meaning it prevents the oscillation. So it prevents the higher peak to lower, and it is making so what you will infer, as theta becomes equal to 1, this should almost nullify this oscillation. Okay, now you will be seeing in the other two cases. Okay. Now look at this. I have drawn with a green ink. Okay, so this one. So this one is not oscillating, and this is the case where theta equal to 1, and that's what we studied here. In this case, case 3, where theta is equal to 1, that means I'm going to get a graph like this. So I have drawn that by a green ink line. So this is theta equal to 1. Now what is a, so as you can see here, as theta increases, the oscillation is also decreasing, and a stage comes when theta equal to 1, totally that oscillation gets eradicated, or we'll say that at this point the system manages just to vanish the oscillation. So it was there till the point theta is equal to 0.99999, etc. Right now, as it reaches theta equal to 1, it just managed to nullify the whole of the oscillation at the output. Now what will happen for the, and I can draw you one more graph, similar to what I have drawn it with the green ink. So this is actually again theta. So this can be, say I am just putting theta equal to 2. Okay, now these are the 4 cases I have drawn. So these 2 cases, since the theta value is in between 0 and 1, you can call that as what? So that condition is called as the underdamped condition. So this is underdamped condition, right? Now at theta equal to 1, so this green thing is theta equal to 1. Okay, this one green one is theta equal to 1. So this is called as, theta is equal to 1 is what we call as the critically damped condition, right? So this is the critically damped condition, that is at theta is equal to 1, and since theta is equal to greater than 2, greater than 1, where we call it as the over damped condition. Okay, so we have seen 3 cases. One is under damped condition, number 2 is the critically damped, number 3 is the over damped. So what is the demarcation between over damped and the under damped, or oscillation and without oscillation? It is theta equal to 1. So that is why theta is equal to 1 is the demarcation point for the system either to be in the oscillation state or without oscillation. Okay, so this is the comparison of the step response of a second order system with respect to various values of theta. Okay, hope you understood.